So the chain rule, we can just review it real quick. In Calc 1, if you're given two functions, let's say y of x and then x of t, if you want to calculate dy dt for a composition y of x of t, the chain rule says that dy dt is equal to what? dy dx times dx dt. Okay, so that's what it looked like in Calc 1. With two variables, now we have z equals f of x, y, and maybe x is defined in terms of t, and y of t is equal to y. The composition z equals f of not x but x of t, y of t expresses z as a single variable. In this case, what? In this case, just t. The chain rule for this situation is dz dt, and we say just not a partial derivative here because if z is expressed as a single variable, then it's just dz dt now instead of partial z or something like that. So dz dt will be partial z partial x times dx dt plus partial z partial y dy dt. Hi, J-Rom. I'm glad you weren't 20 minutes late today.
Yeah, I'm glad to.
If you're not sure why this formula works, you can actually kind of see if you ignore the dt's here. This looks very much like the formula for what? Total differential, just everything divided by dt now. Okay, so it's pretty much related to that. Pretty easy to work with. Things could get a little tricky if there's a lot of stuff being plugged into one another, and we'll go through some tree diagrams that will help with that. For now, let's try this example. That's what happened. 1 second. Let's say z equals x squared y minus y squared. And we know x is equal to sine t and y is equal to e to the t. Let's find or evaluate dz dt at t equals 0. So, using the formula right above, we just plug it in. Partial x would be what? And then now looking at x, dx dt would be cosine t. Good. Plus partial y is x squared minus 2y.
Oh, see that.
Close.
A little off.
Just a little. And then dy dt is e to the t. Okay, but we want everything in terms of t, so now what we're going to do at this point, we use our definitions for x and y, so then instead of 2xy, it's 2 sine t e to the t times cosine t plus sine squared t minus 2 e to the t, bless you, e to the t. And if you want to evaluate, we can simplify more or plug it in now if we want. At t equals 0, dz dt will be 0 plus 0 minus 2 times 1, so negative 2. Okay. Any questions on this example? Yeah.
Why in terms of t? Why can't we just substitute?
You can. Absolutely, you can. Which is why it's like, why do the chain rule if we can just plug everything in right away and differentiate? Mostly because some of the applications that we're going to do later involve using the chain rule to derive some of these new techniques we're going to do. So it's useful to know how that works. But yeah, you're always presented with an option. Unless, of course, on an exam I say, use the chain rule, then you can do it however. Okay. So this idea extends to any number of variables. So if you have w equals f of, and let's say we have x1 of t, x2 of t, x3 of t, and so on, and we wanted to calculate dw dt, you do the same principle we applied earlier. So you do partial w, partial x1, dx1 dt, plus partial w, partial x2, dx2 dt, and so on. These are what I consider, the more straightforward chain rule applications. There are other instances where, well, it gets a little involved. So let's look at some tree diagrams so you can kind of see how those work as far as helping you figure out a chain rule for each situation. So we'll start with the one that we already know. If we have z equals f of a composition x of t, y of t, then easy way to figure out the chain rule is to start with z, and now kind of use this technique of saying, okay, well, z is defined in terms of x and y, but now x is defined in terms of t, as is y. And then as far as determining whether you use a partial derivative or not, it's pretty much in the tree diagram. Going from here to here, there's two variables, so to get from z to x, we'd have to do partial z, partial x. Since x is defined in terms of one variable only, then you can just do dx dt here. Similar on the other side. Okay, so here's an example of using that in a slightly different situation, but let's say z is defined in terms of a function in terms of x and y. And now x is defined also in two variables, u and v, and so is y. What are the chain rules for partial z partial u and partial z partial v? If we do a little tree diagram here, z is defined in terms of what? And now x is defined in terms of u and v. Y, u and v. Good. So now let's just label all the paths. From z to x, we would do from x to u, partial,
Partial x, partial u.
there we go.
Something like that.
What's the difference from what I said?
X is defined now in terms of two variables. Before it was x was in terms of just t, so that's why we did, bless you, that's why we did dx dt. Since here it's u and v, we have to do partial x, partial u. So this would be partial x, partial v. In fact, these are all going to be partials. Do you guys see that? Because everything is defined in terms of two variables. So this is partial z, partial y. This will be partial y, partial u, partial y, partial v. Okay, so now if we want partial z, partial u, oh, this one's almost dead. Just look for where we end up with u and follow the path. So we'd have to do this, and then this way. Does that make sense?
It doesn't matter, right? Like what you do. This is like the same answer.
Right. Well, what do you mean it doesn't matter what I do?
Like it doesn't matter which path you pick, like to find.
Well, we need both of them together. It's going to be a sum, yes. So you're going to add up, yes, both paths. So partial z, partial u would actually be partial z, partial x times partial x, partial u plus partial z, partial y, partial u.
So instead of the dx,
Right.
dt, it's going to be partial.
The only thing that changes in this case is that partial. In the first tree diagram, we had to do both paths. If we want everything in terms of t, then we got to get to t every possible way. Okay.
So, if you were to have like u defined like in terms of one variable, would you just add like a du dt?
Yes. But now, in this case, maybe it'd be more like x would be defined in terms of just u. You know what I mean? So then it would be partial z, partial x, and this would be dx du. Does that make sense? Okay, so all you have to do is follow the paths, and depending on what function you're at, if you're going from one function to two different variables, you have to use partials to get there. If it's just a single variable like above, then it's just dx dt or whatever the variables are. Okay, pretty easy to work with. Oh, we didn't finish this one yet. Partial z, partial v would be what?
Partial g, partial x. Partial x, partial v. Partial z, partial y. Partial y, partial v.
Pretty easy. Okay. So why don't you guys try this example? Let's say z equals 2, whoops, started to write partial. Z equals 2xy And let's say x equals u squared plus v squared, and y equals u over v. Go ahead and find partial z, partial u. And if you're done, might as well do the other one too. Now since u was defined in terms of u and v, your final answer for partial z, partial u should also be in terms of u and v. Similarly with partial z, partial v. oops, partial z partial u will be partial z partial x, pretty much same formulas from before. So then that will be 2y times 2u plus partial z partial y. So that'll be 2x 1 over v. And now we replace y with u over v and x with u squared plus v squared. So some of you have two separate fractions. I wrote it as one since I saw that there's a denominator of v. So 4u squared plus 2u squared plus 2v squared all over v, or equivalent. Some of you had it as two terms, which is fine. Partial z, partial y, or partial v, sorry.
But where did the 2v go from your thing? Is this like over 2v?
Two.
Oh, right, okay.
Are you sure?
Yeah, now I get it, yeah.
Okay. Sorry, I wasn't sure what you were pointing at before. Okay. Partial z, partial v. It's partial z, partial x. So that's 2y again. And now this is times 2v plus 2x. And then minus u over v squared. When you do partial y, partial v, replace y with u over v, x with u squared plus v squared, so what did you, some of you had 4u minus, I'll put the minus out, so then 2u squared plus v squared over, some of you left it like that, that's fine. Oh, forgot the u. There we go. So you can leave it like that, or you could combine it into common denominator, which is what I've been doing. So I put everything over v squared. So this is 4, no, but I'm just in the habit of doing that. And then this will be minus 2u cubed minus 2uv squared. Heidi, you okay?
Yeah.
Okay. All right. I think we can leave the rows and the fees and all that for later. It's the same concept. Here's one that we should try. Find a rule for dw dx if w is xy plus yz, y equals sine x, and z equals e to the x. Okay. So this one's a little different, and you can see that because we have w defined in terms of x, y, and z, we don't have an x function. We do have a y and a z function, however, and those are defined in terms of x. So it's a little different. If we look at a tree diagram, I mean, some of you can probably already know or probably already have a way of finding dw dx, but this usually helps me. So if I have w, which is defined in terms of x, y, z, my goal is to finish in x This is already good, so that path's done. However, y is defined in terms of x, as is z. So then to get to all those x's, this would be partial w, partial x, partial y, or I'm sorry, partial w, partial y, and then partial w, partial z. To get from y to x, it is dy dx, and then to z, from z to x, dz dx. So then the formula for dw dx can be calculated by doing what sum? Dy dx. It's hard to say all this stuff, isn't it?
Partial w, partial x times dx, or dz dx.
There you go. Alright, so there's our chain rule formula for this scenario. Now we just find them. So partial w, partial x would be just y, plus partial w, partial y is going to be x plus z, dy dx, cosine x, plus partial w, partial z, well that's going to be y, and then dz dx is e to the x. We want everything in terms of x's. Y is sine x, z is e to the x. So I'll do e to the x sine x here. That's good. So I mean, these are not difficult problems. I think you'll probably find the homework is not so horrible this time. Okay. We only have one more thing to do, which actually, this is now one of the reasons why it's nice to know what chain rule is, because it might make life a little easier for some other things that you guys have been doing. Are there any questions so far? Okay. All right. So let's talk briefly again about implicit differentiation. So here's a scenario which you already know how to do, but let's revisit it with a different approach. So let's say we have y cubed plus y squared minus 5y minus x squared plus 4 equals 0. Here clearly y is defined implicitly, but let's say our goal is to find dy dx. Okay, so in the past, you would do implicit differentiation, and you'd do everything, maybe some product rules, and so on and so forth, depending on how involved the equation is. Let's revisit it with multivariable calc. So let's start with the fact that we can call this a function of x and y, because it's defined in terms of x and y. And we'll just say 0 is 0. Let's just call it a constant, because really it could be any constant, and then the idea is still the same. So now, if we want dy dx, same idea that we've been working with. F is defined currently in terms of x and y. X is good, but y is defined in terms of x, since we're saying that this is a function defined implicitly in terms of x.
Wait, huh?
How did you determine that?
Yeah.
Um,
I've not seen it.
it's that you don't. That's what implicit means, is that you don't see it.
No, that's more than that.
Okay, so y is a dependent variable, right? Typically, we have functions defined in terms of x when we have y. Okay, if in fact we have y of x equals, some stuff with x's x stuff, that means it's explicitly defined, right?
Okay.
Here, we have y's everywhere. We could rearrange or try to rearrange the equation so that y would be isolated so that we can get an explicit equation for it, but we can't. Okay, so because our goal is to find dy dx, and because we're treating y like we did in Calc 1, where y is dependent, we're saying that y is still a function of x.
So if it was like z, it would be implicit.
X and, yes. Yep. Okay. That's about as good as I can do. We'll figure something out later. Yeah.
It's fun.
Would dx dy be, y would be defined explicitly and x would be
Yes.
implicit?
Yes. So Roma asked a good question, which might help clarify. If we were looking for dx dy, now we're treating x as dependent. Okay. So in this case, we'd say f is defined in terms of x, and x is defined in terms of y. And then y would just be y. It all depends on what the dependent variable is in the derivative. Okay. So from f to x, that's partial f, partial x. Same with f to y, partial f, partial y. But now since y has just one variable, that's dy dx. So we have that partial f, partial x plus partial f, partial y dy dx equals 0. And now we can isolate dy dx. Dy dx would be minus partial f, partial x over partial f, partial y. So now you have a nice shortcut to find a dy dx when y is defined implicitly. So instead of doing implicit differentiation, if we look at a quick example, you'll be done in about a third of the time. Okay, so let's say we have, I don't know why I did that. This is the scenario we had. What is partial f, partial x? Negative 2x, right? And then partial f, partial y would be 3y squared plus 2y minus 5, and we're done. This is our dy dx without having to actually do any implicit differentiation. Okay, so this is just one application of where the chain rule can be used. So now we have a nice little shortcut. Your Calc BC friends will be amazed that you can do things very quickly compared to how they are doing it currently. If we have a function in terms of 3 variables, the ideas are similar. Here are their formulas. Partial z, partial x will be minus partial f, partial x over partial f, partial z. Partial z, partial y will be minus partial f, partial y over partial f, partial z. Yes?
Is it partial z, partial x, or dz dx?
It's partial z, partial x, because now z is defined in terms of x and y. So, I mean, I'm not going to do it now because we could still, same idea, and then isolate the derivative that we want. This is the formulas that we would obtain. Yes?
How come, like, if we, like, look at those two bottom equations,
Yeah.
if we cancel, like, partial f's, we should partial s for partial z.
You can't cancel the partial f's. This, I know this looks like a fraction, but this is like one whole derivative, right? However, that presents a nice way to remember the formula, right?
What the opposite?
Confusing way to remember.
Yeah.
Well, whatever works for you. I mean, when you said
To
that,
remember the formula.
I just remember that the x's and the z's switch, and then it's just partial f. Negative. Yeah, not very helpful. Okay.
I can kind of see that.
It works for me, all right?
All right.